Okay.
So welcome back, everyone. Now we have Gagik, Gavalian, who's also a JLab staff scientist,
Yes.
and he will keep talking now about artificial intelligence for us. Now that we'll have
Unless you guys are tired of it already. then we can
introductory.
All right. So my name is Gagik Gavalian, and I'm staff scientist at Hall B, Jefferson Lab, working with CLAS12 Detector. And this is my talk. Thomas gave a very, very good introduction to neural networks. So I'm going to concentrate on, my talk is going to be slightly different. What I'm going to do actually is introduce you to a problem and show you how we solve this problem and what kind of networks we used and actually what kind of activation functions we used, the question that was asked. And this becomes important because in more practical sense, when I started doing these things, there are no guidelines where to apply your artificial intelligence, right? If you have a specific problem, you don't know what kind of network to use. You don't know what will work for you. And well, you essentially don't, especially in a field of physics, you don't know where to start. If you're analyzing images, everything is peachy. You Google image analysis, they give you everything that you need to know. But for physics, you will see some specific problems and how we solved it. So I'm going to give you a brief introduction to machine learning, multi-layer perceptrons, convolutional neural networks, extremely randomized trees, gradient boosted trees, long short-term memory networks. And then I'm going to tell you about the applications in physics, how we got started and what problems we had and how we solve these problems using neural networks. And then, yeah, and this is it, yeah, different types of networks that we use, the classifier networks, linear regression, logistic regression, series predictions, and autoencoders. And you'll see where everything is applied, right? All right, so this is sort of encyclopedia thing of machine learning, and Thomas already told you what machine learning is. It's essentially learning, building a model based on some data sample, which is called training sample. And with that model, being able to do predictions on a different data set, which is called the test model, without being explicitly programmed to do so. You just give it the data, and it has some neural connections, and it does the job. It predicts the outcome for your data. And again, this is, Thomas already talked about this, the way it's done. You are training your network by going forward pass, calculating your function based on your input, you're calculating your output, applying some activation function, and then you are calculating your loss being how close you are to real answer that you are expecting. And you're calculating derivative and doing backward pass, updating your weights, and then going again. And the more you do it, the more network learns to replicate your data. But then there are some issues with overtraining, and I'll tell you how to overcome those problems. But in general, this is how it goes. You keep learning these weights until your for any given test sample numbers, your output number closely matches what you expect. And this is with activation functions. You see, he showed you only the sigmoid version, but there are tons of activation functions, and every day they come up with new ones. So this is the standard sigmoid one. There are tangent. There is ReLU, which is used a lot in image classification. This is rectified linear unit, only has positive. This is leaky ReLU, ELU, and max out some things. And a priori, actually, you don't know what will work, but I'll show you how you find out on this thing. And there is another one that actually not mentioned here is so-called softmax, which is the most used one in classification problems. And this is from your network output, logistic output, everything gets normalized to 1, because logically, if you are making any kind of classification, the probability of being everything should be 1, right? So one of them has higher probability, one of them has lower probability. So what you do, you choose the highest probability. Like in this case, it's not really telling you that it's a dog. It's telling you 77.5% probability is dog. Well, it could be a cat, it could be a horse. I don't know why it says it's horse, but it's in Google English again. But I'll show you some techniques how you actually maximize your output based on your training sample and how to deal with this kind of thing. All you have to remember here is that for the output, you use either softmax activation, a layer for the output, or one of these. These are the most popular ones. There are some other ones we can see. All right. And then after you do some classification problems, you also have to judge how well your network is working. And then they have some metrics which is telling you whether your network is performant or not. And these are called sensitivity, accuracy, precision, and the way you calculate it, this is called the confusion matrix. You construct confusion matrix and you count how many times you predicted accurately what that image was. That's called true positive. How many times you predicted negatively, like it was a horse and you said it's not a dog, that will be true negative. And then you also plot here your negative results when you identify falsely the negative sample and falsely the positive sample. And then you have these formulas, which is the sum of your good predictions, whether it's positive or negative, divided by the total sample. That will be accuracy of your network. You have precision, which means how well you are predicting the right answer. You have sensitivity, which is sort of the same thing. And then you have a negative predictive value, which is essentially showing you how many times you make mistake, proportion. Okay? And this is called confusion matrix. If you see this square thing that's showing you numbers, you know, always the diagonal is the one that is true positive, true negative. And on the sides, you have false identified, either false negatives or false positives. So for multi-class things that you are identifying many outcomes, not only dog or not a dog, but you want to identify dog, cow, camel, or something, then you construct the confusion matrix n by n, depending how many classes you have. And again, the diagonal is showing you your real predictions that it was, I took this image from Google, so I don't know what Luad and Luad is, but you get the point. Diagonal shows you your accuracy level, and this is actually what you calculate in accuracy is the sum of the good predictions divided by the entire sample. This is, for example, you can judge from here that this is network is 94% accurate predicting right one. Okay. All right, and then there is another metrics that you actually want to know about, and you will see in a plot when we are testing the accuracy thing. If you notice here, this is giving you a probability of something being of that class, right? And because this all adds up to 1, if your value of this is above 50%, meaning that adding all the other values that is below 50%, right? So you can confidently say that if something is above 0.5, this is my class. But sometimes, well, that's what naturally is done. And there is such a thing called the ROC curve, which is a receiver operation characteristics. It shows you how well you are, what percentage of good predictions that you are doing, depending on where you put the cut. Sometimes, because there are sometimes problems when you don't necessarily want to know whether this is a dog or not dog, but you definitely want to cut out things that are not dog, right? And in that case, you actually might want to move this threshold to get rid of as many not dogs possible as you can, leaving some noise there, but you want to 100% to detect your dogs, whatever noise it comes from. So this is actually, you construct this ROC curve, and then you can match depending on where you place your cut to get all the dogs included in your output sample. And this actually shows you where to make this cut. You have to construct it. Essentially, this is measuring how many true positives you have depending on where you put that threshold cut on the probability of the label. Okay. So this is just following what Thomas was explaining, introduction to all the different terms and all the different concepts that we'll be talking about. And now we will switch to physics problems and what we are doing with how we are solving this. So let me just introduce you to Jefferson Lab. You are now at Jefferson Lab. This is accelerator facility where you have an accelerator that's running at 12 GeV, and it has 3 experimental holes that is supplying beam to electron beam. Actually, it's a photon beam to whole D. But and 3 of these holes can operate simultaneously during the year to run experiments. I work for hole B, where CLAS12 detector is located. And CLAS12 detector, we are measuring essentially electron scattering on liquid hydrogen, and we are studying the structure of the proton or some new excited states of the nucleon. And this is sort of side view of the detector. It consists of many components. It's 4-pi detector in a forward direction. It consists of 6 sectors, drift chambers that measure particle momentum, charge particle momentum. It has some time of flight system. This is the orange one here. And this red one is calorimetry that is detecting photons or and tagging electrons and neutrons. And then it has also a central detector, which is detecting any particle that is flying sideways. It's also a tracking detector. And I'll show you in details with us. And this is all inside of the toroidal magnetic field. So particles, charged particles can bend. And that's why how you measure their trajectory and their momentum, you infer their momentum. And this is the side view of this. This is sort of a slice, and you can see two sectors of drift chambers, which consist of 6 independent chambers. These are the chambers, 1, 2, 3, 4, 5, 6. And you are measuring the trajectory of the particles, charged particles going through these chambers, reconstructing, fitting them with a Kalman filter, and then that fit gives you the particle momentum. And you are once you reconstruct all the particles, you start doing physics with it. Right? Now, and also here, yeah, and this is a solenoid magnetic field where you have a central detector. It's not drawn here, but essentially, I'll show you later. It's a barrel, silicon barrel that measures again heats as the particle travels through that, and then you reconstruct tracks based on the positions of the heats that you have in the chambers. All right, so now let's go to multilayer perceptrons. This is one of the simplest networks that Thomas was explaining. So multilayer perceptrons are just flat layer of numbers with the input vector x and with the output vector y. The number of inputs and number of outputs don't have to be correlated. They can be any number, can be the same. That doesn't have to be. And consists of hidden layers with each neuron connected to every neuron in a hidden layer. And then these activation functions are calculated for each subsequent layer and then added up, and then you arrive to some answer. So connected layers activation function can be anything here. ReLU, sigmoid, tangent, linear, or softmax. Softmax are usually used in the end if you are doing classification. And this kind of network can be used for different things, like for classification, linear regression, logistic regression, or fault correction autoencoders. And now we'll go with classification problem. Now, when I showed you the drift chambers, actually, there is a problem there. So these drift chambers are used to track charged particles. As you can see here, these are the heats in the drift chambers. And this is how, once you identify which heats belong to a track, you can confidently feed them because there is a magnetic field here. And then you derive the momentum and the angle, polar and the azimuthal angle of these things, right? And it consists of 6, we call them super layers, but they are separate drift chambers, and each chamber has 6 layers of wires. And each layer has 112 wires going along this direction. And this is how it looks like, the raw signal looks like in each chamber. This is just one sector, one slice, 1/6 of the azimuthal angle from the 60-degree angle, right? And as you can see, you have each chamber is measuring one segment of the track trajectory. And you have many segments from this. And what you have to make is you have to make a combinatorics of which segments belong to a track. Right? You are constructing tracks from 6 segment combinations. And the problem with this is that when intensity of the beam and the number of interaction increases, the combinatorics becomes very large. And what you have to do is you have to consider all the combinations, which sometimes it goes to thousands, and make a judgment. What do you think is a good track? And what you are doing is you are doing some simple polynomial fit to see. And you can make mistakes there. And the mistakes are usually on order of 15% of the time you can be wrong. And then when you go to the final state, when you are doing nice fits to reconstruct your momentum, you are losing those tracks because you identified wrong clusters for this. Right? And this is just showing you how this looks like. This is just the image of one track leaving trace in all of the chambers. Like I said, 6 wires in each of the chambers. And then you have 6 segments that comprise the track. And what we do is we are dealing with segments for the neural networks where as an input, we are using 6 numbers, which is a mean position of this segment along this wire thing, which is, this is 112 wires long. So we are essentially calculating mean of the first 6 wires, and then mean of the second 6 wires, and so on, and we end up with 6 numbers here. And what we want to do is this classification problem. We have this many combinations. This is showing you a little bit squeezed view of this. So if you have this many hits, and the black one is the right combination actually that the track left, if you connect all of the 6-sector tracks, these red ones, you end up with many combinations. I think there are 29 here. And then you have to make a judgment which one is a good track. And what we do is we train we make a network, a classifier network, which again, this is all the nodes, connecting nodes are with activation function ReLU. And in the end, you have softmax to tell you whether this is a positive track and negative track, or this is not a good track. And what we do is we make a training sample by taking two tracks that were reconstructed, fully reconstructed by reconstruction algorithm. We know they are good tracks. And we are giving them, you remember Thomas was saying that you have to keep balance between negative samples and positive samples. So for each positive sample, we are giving another negative sample by swapping 2 of the hits from the other track, 2 of the segments, and giving it as a negative sample. And the reason we are doing this is the following, because if we take any random hit and give it as a negative sample, random sample, you are running a danger of giving a good track as a negative sample, and that will affect the network. It will actually, in the future, when it sees a good track, it can think it's a negative thing. By choosing really good reconstructed tracks and swapping this, you are making sure that there is no good track goes into negative sample. This is done intentionally, okay? So we are doing this true tracks, false track, true track, false track. So we make 4 samples out of this true track combination, and we train the network with this. And we actually try, yes.
So, I mean, in the case of the 2-track samples, I would understand if you switch them, you will get a negative one. But in reality, you have much more tracks, right? So if you switch them, there is still a finite probability that you will get a good track.
No.
Even if there are more tracks. This was a 2-track sample.
No, we take only events that have only 2 tracks. And then we swap them to make a negative sample. So no, there is no probability, because we know these two tracks are good. If this is a good track, and from another track that doesn't contain the same segment, you swap it, it cannot be a good track.
So you always take events with only 2 tracks?
Yes. Yes. Yeah.
So is the position resolution in the drift chamber good enough that a good track will always be?
Yes. Because one of the things, this was actually a real event. This was not a mock-up. Usually they leave a trace signal in 1 wire, right? And so an average of this is within 0.36 wires accurate. So yeah, you cannot have another track going that close to the track.
So this is not the same particle.
Sorry?
Like the 1 and 2 is not the same particle. As
this one? Yeah, no. There are 2 different particles in an event that.
Well, and then the last one with the real. Yeah.
This one?
So this is like 3 different particles?
No, this is 1 particle. This is 1 particle. I was just showing you for 1 particle how we construct this vector. Okay. Now, what we take is a 2 particle event. So two of these things will be on this picture. Yeah.
If I may, I think there is a space between superlane 1 and 2,
Yeah.
3 and 4, and 5 and 6. So
This is why I have this. So 1 and 2 in space are separated by about 1 meter. Here they are separated by 20 centimeters. So they are far apart. Yeah. They are just made into this one image-like form that is easier to see on it. Yeah. Okay. So we tried a few different networks, but I'll talk about different types of networks later. We ended up that MLP is giving you best true positive, which is 99.96% probability, and false positives are about 10%. So we went with this thing. But now, before I show you what this results in, I want to talk about autoencoders, corruption autoencoders, actually, which is also using MLP network. So when I show, and this is a 2-track event, this is how the 2-track event looks like. So in some points, this is a physics detector, right? We are dealing, when Thomas was talking about some inefficiencies, when you have some lost things in your detector, sometimes what happens is that one of the segments is missing from the track. And this is inefficiency in the drift chambers. But our network is trained to accept 6 inputs to give you a valid, to make a prediction whether this is good track or bad track. So what do we do with this? How do we identify these kind of tracks? And these are actually very common occurrences. There are 15% of the tracks come with a missing segment. So one of the first ideas that we had is that we can design a network that takes 5 as an input and then give it a track. But that didn't work out really well because the segment can be missing here or here or here. So it gets very complicated and the network gets confused very, very easily. And what we decided to do is to use autoencoders to do corruption recovery, essentially. And I'll talk about what autoencoders are. So yeah, and this is what I'm talking about. So this is the same example, and here you have a missing kit and you cannot connect them. You don't know how to fix it. Now, autoencoders. This is one of the most interesting networks, and Thomas actually briefly mentioned it, but I'll tell you what it is and how it's used. So what an autoencoder is essentially the same thing. You have an input layer and output layer and connected layers. The main difference of autoencoder is input layer equals exactly the size of the output layer. And what you want to train the network is not to give you answer to the inputs that you have, but it returns the same input vector, the same size, slightly modified, right? You want a different representation of the same thing. And these things are autoencoders are mainly used for denoising and for this kind of thing. For example, if you have a face, you want that face, but without the noise. So it's exactly the same thing, but some of the pixels altered. And it's also used for this handwritten database called MNIST. I don't know if you are familiar with this, but if you have a handwritten digit and you are reading off of the paper and you have noisy paper, these autoencoders are used to reproduce the same image, but without the noise. They are used actually in some places to color images. And again, the input is the same, output is the same, but some states are altered, right? You have the same exact thing, but in color. And they are used in MRI to actually get rid of the noise in the brain images when they are doing diagnosis. So these are helpful things. So all you have to remember when you are hearing this word autoencoder is that input and output are the same size, same thing, with the things altered, right? Changes something in between. All right. So when we discovered this, actually, it's advertised in Keras library as something. You take something noisy and then you produce something not noisy. But then when we're thinking about it, can we actually go backwards? Can we take something that is not noisy and add something to it, not remove it? So this is essentially a network that removes something and produces a cleaner version of that. But what we want is actually the opposite of this. And so what we want is something that is not there, and we want network to add there, right? And luckily, time reversal works, actually. It did work, and I'll show you how we did that. So what we do is we take one of these tracks, again, which is fully reconstructed, non-corrupted, and we corrupt them on purpose, and we corrupt them with all possible ways, like removing first point here, and then removing the second point here, removing the third point here, removing the fourth point here, fifth and sixth, and we are making the training sample. So for this, I want to get this. For this, I want to get again this, right? And we make all millions of events of this kind of things. For each valid track, we produce 6 samples. Again, going back to, you have to have balanced data set so it can figure out for each particular case what to infer, right? So we made this complicated training sample, and we trained this autoencoder, again, with this kind of structure. And after we trained it, we decided to test it, how it looks, how it performs. And what we found out that in average, it can predict the position of the cluster of the segment. I use interchangeably the cluster and segment position within 0.36 wires, which is much better resolution than actually drift chamber resolution. When they are clustering, they have resolution of about 2 wires, closeness of the cluster. So it can actually predict very well where the heat position should have been. And this is actually image of prediction as a function of where that node was missing. So this is first super layer, second super layer. So this is done to see if there is any bias between if it's missing on the last one, it's performing better, if it's missing in the middle or not. But we found out that if you project this, there is not much difference. It's a little bit going off and on here, but this is just a eye effect. It's within 1 wire, it's able to predict it very well, well within the accuracy of segment prediction. So after we had that network, we combined these 2 networks together, and we did the following. We wrote an algorithm that from any given sample of combination, it chooses the good tracks with 6 segment combination, removes that from the sample, and then runs through the second network, which creates a pseudo segments based on five segment combinations, and then starts evaluating each of them with this first network that was used to classify events, and then finds the second track that was, this hit was generated pseudo randomly with autoencoder, and then reconstructs the second track too. Okay. Once we put these two together, we run our reconstruction again, and we found out that now reconstruction reconstructs about 15% more tracks than the conventional algorithm could do. And when you use it in physics, this is showing the neutron reconstructed as a missing mass of reaction. Electron scattered on a proton produces E prime, pi plus, and neutron. X is missing neutron. And this is a three-particle final state with a missing proton. What we found out that increase in single particle efficiency of 15% resulted on about 20% increase in statistics in two particle events, and about 35% increase in statistics in three particle events. Okay. So, and this is ratios of the conventional algorithm versus AI assisted. We call it AI assisted tracking algorithm. And this is about 20% here, and then about 35% here. Let me put this in context, actually. To run an experiment like this, JLab spends about, DOE spends about $8 million a year, right? Now, with the AI, we increase the statistics 35%. You needed to spend $12 million to get these statistics. You guys can do the math, right? How much they, yeah.
So are you saying that without this algorithm, if we reconstruct it in a traditional way, some structures go to loss
because of the combinatorics, yeah, we cannot resolve the combinatorics.
But with this algorithm, we can pick up more tracks from the background.
Yes. Yes. Yes.
So I was in RGM and I kept hearing people talk about DC roads. Is that what this is?
No, DC roads are actually something that you simulate a database of possible roads, and that's used in a tree. Yeah, that's not what it is. And it cannot give you 35%. Yeah.
Have you tried doing these studies with missing two non-consecutive superlayers?
No, but that's a good point, and we're going to start doing that because now we are trying to do the same thing for the central barrel, and that one has two missing ones. But the thing is that even if we identify tracks that have two missing segments, the leverage of the track fitting is not enough to reconstruct the resolution track, so we don't actually need that. But for the central detector, we're going to do that. Yeah. Okay, so this part is about finding tracks, MLP, right? Now, linear regression. So far, I talked to you about the classifier, corruption, autoencoders. Now, let's talk about linear regression. Again, using an MLT probe, multivariate perceptors. So this is, again, drift chambers and showing you different tracks. This is all background, and the red ones are identified tracks. And now we can clearly identify from the background, from all the hits, where the tracks are. Now, the question is, can we actually reconstruct their momentum using neural network? Because the conventional algorithm spends about, give or take, 750 milliseconds, almost a second, reconstructing one track, right? And you take about 11,000 events per second in a data acquisition. So that's a long time. If you are running your experiment for 1 month, you take about 6-7 months to reconstruct the data. It would be nice if we can reconstruct the data right on the fly, right, when the experiment is going. So the simple thing, we run some tests to see how the tracks look like when you are at the same angle you are throwing tracks. This is Monte Carlo doing just for illustration purposes. And they have different momentum. And these are tracks with the same, going in the same angle. 12 degrees in a polar and then 68 azimuthal, and have different momentum. And you can see that they have distinct, different mean values of the segment. And this is same track with the same momentum going at the different angles. You can see these are distinct too, right? And then we did this, made this neural network, which has 6 inputs, again, average values of the segments going through each of the super layers, some hidden layers. And then we want, in the end, not a classifier, but we want a linear regression, which is outputting the momentum, the polar angle, and the azimuthal angle, right? Now, your question, like, what do we use here? Like, what would be your first guess to use? We have like 6, 7 activation functions, right? And 6, 7 output functions. And the answer is everything. Right? I'll come to that. So the way this is done, and again, this is going to neural networks. Thomas didn't mention, or mentioned it briefly, I didn't notice. But everything, when you are dealing with these activation functions, they are defined in a range from 0 to 1, which means that you have to normalize your data sets to 0 to 1. And what we have here is, I'm showing you, this is average wire position of the segment that went for this green track, and normalized 0 to 1, that will end up with 0.25, and the output was 0.7 GeV momentum, 12 degrees theta, and 60 degrees phi. This translate into these numbers, which are also 0 to 1, and then for the red track and then blue track. So these are your training samples, right? And what you do is you run your network with all kinds of combinations of activation functions and output functions to see which one works. We actually a priori didn't know work, and I thought that this one, ReLU or linear, should be the best one. But what we found out that best performing one was the tangent and the linear function. And this was the result. This is as a function, this is a resolution of how well you are inferring the momentum and the angles as a function of momentum and the angles. Once you put this all together, you take the sample and then you reconstruct your momentum using your neural network, and then using your conventional algorithm, and you plot it against the other, and it looks like a one plot because they're sitting right on top of each other. So you cannot see any difference. It's actually, this field histogram is simulated data, and this thick line is what AI reconstructed, right? Now, and then we put it on top of the distribution that was reconstructed by the conventional algorithm. And the funny thing is, it actually reconstructs the momentum much more accurately than a conventional algorithm does at the early stage of heat-based tracking. Okay, so you can actually, with a neural network, identify the tracks, reconstruct the momentum, and do it better than your tracking can do in about half a second. And you can do this with with 34 kilohertz rate. Essentially, while you are data taking. So think about it. Right now, it takes 1 month to collect the data, right? It takes about 6 months to process it, and then you can actually plot your distributions and look how your physics looks like. Now, with these networks combined, these 3 networks, you can do it online. You can click a button, and online it will show you your physics reaction and your distributions. Is it cool? Okay. All right. Now, yes.
Is this actually being used?
Yes, absolutely.
Like, it's
So,
the experiment that happens in Hall B, whenever that starts, it'll do this.
yes and no. So,
Okay.
so this part, yes.
Okay.
This part we just finished with my students. This implementation, it's in implementation stage when we're gonna start putting it online. So maybe not the experiment that's not running now, but the next experiment, I promise you, yeah, we're using it. Yeah, but we have the other one. Once you start reconstructing it, you're going to get 30% more data, and that's a grassland. That's yeah.
So in the experiment, that it's found that this algorithm has been implemented. Is this usually one even only have 2 or 3 tracks?
Which one? This? No. That was for training purposes.
Okay, but in practice, when you use it in the real experiment,
Yeah.
there are much more tracks.
Oh yeah,
And
absolutely.
okay.
Yeah.
And
Where was this? This one had 3 tracks identified, right? This scattering experiment, we detected the scattered electron on pi plus, pi minus, and we're looking for the missing proton. Yeah, ask me as well. Yeah.
Yeah, so because you put it to use in a much more, I guess, complicated tracks, right?
Yeah.
Do you need to train it with more like complicated samples as well?
No. It identifies every single tracks, and it can pick up 2 tracks in one sector, 3 tracks. It does not. It looks all combinatorics, but instead of using a fit where it can make a mistake, it's just making judgment which combination of segments is the best fit. And that's all. You can reconcile as many as you want in a sector or in different sectors. And yeah.
Oh, sorry. Oh, okay. Yeah, because in principle, everything is just linear computation. Right? So you can kind of extract as many tracks as possible.
Yeah.
From the noise.
Yes. As many tracks as there. Yeah. I cannot extract more than there are there.
Yeah, of course. Right. Yeah.
Right.
Sorry.
Yeah, so this is going to be applied retroactively too, right?
Sorry?
This is going to be applied retroactively too.
Oh yeah. So. Right. So, everything is going to be retroactively applied. For example, this one is already applied. A new cooking is, we call it cooking. Data processing it includes this thing, but also in class 12 we have so-called trains, which after the data processing you run your data through the trains that isolates events into different physics, right? And now, once this network is in place, we can actually isolate this event even before data processing. So, yeah, we can use it after the fact too. Once the data is collected on the raw data, you can do this momentum reconstruction, separate your events depending on your reaction, and then work on much smaller sample processing data. Yeah. So now, one thing I wanted a little time. This is just to finish the MLP part, and then. Tomorrow I'm going to talk about more complicated networks and their applications. But here, one of the important things here is how you train your networks. Nobody actually on the web tells you all the pitfalls that you can fall into when you are training network. And I wanted to show you this thing. You find it. The neural network has actually a hard time deciding what is this, Chihuahua or a muffin. So, because they look alike, and you have to be careful about these things. And next example I have here, let's assume that you want to train a network that recognizes cats, right? And this is your training sample. You give 3 cats, and you give these appliances as a negative sample. And then you train it, and you say, okay, these are cats, and this is not a cat, right? Good. So now you have this guy. What do you think network will classify? Cat, right?
Yeah.
I can assure you he's not a cat. This is Watson. It's my dog. He gets really upset if you call him a cat. You see, he's upset. So one of the things is that when you are creating the training sample, you should actually give a special care to your negative samples, because everybody knows what the positive samples are. But introducing negative samples, depending on how you introduce the negative samples, that can actually largely affect of what results you are getting on a normal data set. And that is shown actually here. So we had a choice actually how to choose our negative samples. This is again, same example shown. This is a real track. This is a real track. And then when I said you are switching one of the segments, you have choice how to switch this, right? So one of them can be, we call it closest neighbor. Essentially, you switch it with a segment that is closest to the real segment that belonged here, and not others, none of them are touched. Or you can choose a random combination of these things that you do. And you can actually choose a least likely to be tracked, which is we're calculating Euclidean distance between that candidate and the real track. And you can give this, you can give negative samples with this method. And it turns out that when you train this network with these 3 different negative samples, but exactly the same positive sample, you get actually completely different results. And these are the results. This is the closest neighbor sample when you train it, and then you evaluate a testing sample. And what you get is the false positive rate is about 1.3%. Random, actually, if you pick random from those combinations as a negative sample, you get a false positive rate of 12%. Least likely is you get 36%, which is really bad. And the explanation for this is that if you give this random, least likely sample that looks nothing like a track, if it comes to this, I think it's going to think that this is a good track, because out of this one and this one looks more like a track than not, right? So it can actually make more mistakes for positives. In all of the cases, it's actually pretty good of reconstructing the right one. But you also want to minimize your false positives, because that way that can get into the list of the tracks. It's gonna, your algorithm is gonna spend time. It eventually will get disvalidated by the algorithm, because it's gonna fit it and it's gonna find bad chi-square, and it's gonna discard that track. But we want to spend some time, and you don't want to do that. You don't want to overload your algorithm, and it also actually can make a mistake choosing the bad track over the good track. So you don't know. So I think that's my time, right?
You have actually 1 hour. We started.
Oh, I thought 45 minutes. Okay.
I mean, we can have questions.
I think it's better question, because I'm getting into completely different things after that.
Okay, yes.
But let me summarize this thing. So for the classification. Oh, this is wrong. 50. It should be 50%. Okay. So what we have to take it down from the. Okay. So far I introduced you to completely three different things that you can do with NLP networks, with multilayer perceptrons. Right? One, use it for classification, and I showed you an example of that increases single track efficiency by 15%, actually 12 to 15%. Autoencoders that are fixing the corruption and accounting for the inefficiencies that you can have in drift chambers, and then with the aid of this classifier can increase your track reconstruction, which is, this is the right one. So all the combinations is resulting in a 12 to 15% increase in a single track efficiency, and 15 to 35% increase in the statistics, depending on your final state of physics outcome. This is shown here. And I showed you a linear regression that actually uses linear regression type of network, and using the segments from the tracks that were already identified by classifiers to infer their momentum and angles, and then construct the physics quantities, right, with the rates of above 30 kilohertz, way above the data acquisition time, so you can do actual physics analysis online. And that's how you use NLP networks. Any questions? Yes.
In the for example, in the tracking system, you will have like some track and some backgrounds that you have in the detector. Do you like assign particularly the background in the feature of the your tracking model?
That's actually in the next chapters. We have convolutional denoising autoencoders. So, tomorrow.
Okay.
That will answer tomorrow. Yeah.
I think you already mentioned it, but can you explain a little bit more that why the traditional way fail to identify those tracks? Is it because they cannot deal with missing wiles? If you have only 5 points, they cannot do anything.
No. They can deal with missing segments. No, that's not the issue. The issue is, look, so these are actually from a real event. So it's a little bit more condensed. But the initial, the way the tracking algorithm works, you have initial segments and you construct the track candidate, right? And what you do is you do polynomial fit. And polynomial fit is not precise. It doesn't include timing information from the wires to adjust the track very well. So the chi-square that you get from there is has large tails essentially. And you can confuse a track that, for example, instead of this point has this point, with a real track. And once that track gets identified as a real track, goes further into a reconstruction chain and goes into a Kalman filter, which is doing fit, considering all the timing information from wire chambers, drift time, time to distance functions, and all these things. This fit doesn't converge, and the track gets thrown out. So if you are unlucky and some hits come very close to your, let me show you back. Normal from drift chambers, I had this thing, right? Like, for example, this track will get lost, right? You see, there is a segment here and there is a segment here. And I can almost guarantee you that it's by chance that it can pick the one, depending on the order. Sometimes we've seen this. When you change the way you start looping through the clusters from the left or to the right, the wrong one gets picked, and then you lose the track. AI doesn't make that mistake.
I thought you said you're gonna try all the possible combinations.
Yes, you try all the possible combinations.
So, yeah, so if you try combining, are you saying like if you pick the left one over the right one,
Yeah.
it will get lost, it will get, moved
So
on?
this one, let's say the middle one is the right one, right? The right one fitted with this line can give you better chi-square because chi-square has large tails. You don't know just by the polynomial fit, and then you stop even considering. Now, if you come from this one, it will give you a good chi-square that is within your two sigmas, and you will take this. You won't even consider this. So maybe there. One of the other things is that there is some sacrifices that you have to make. How many iterations you do in track fitting when you are doing the track candidate classification, because if you do it very precise, it will take really long time. So you're kind of sacrificing the efficiency to do as fewer iterations as you can when you are doing fitting to converge on a good track. So conventional algorithms have their limitations.
Sorry, but even you identify the wrong one, like you didn't pick the middle one, you pick the right one, you still reconstruct the track. Why
But
then
that's the wrong track.
But you won't know it's the wrong track, but how will it decrease your statistics?
Yes. So if it's a wrong one, it has a wrong momentum. Then if it was in this peak, it moves here, right?
Oh, okay. I see. Okay.
Some of them are wrong momentum. Some of them get discarded at the time-based level when it's doing more iterations with the carbon filter. So it's either or, but either way, you're losing statistics. So this is real data. I mean, what you are able with the conventional to reconstruct is 35% less in a peak than you actually have.
More questions?
Oh, which one? Momentum. Okay.
You use both both neural network or only the momentum reconstruction?
What do you mean both?
You are on the good part of the for having the dark line.
Yeah.
Did you use just the momentum reconstruction network, or did you use the classifier and the momentum reconstruction network?
No. Just momentum reconstruction network, right? So this is because if I use classifier and momentum reconstruction, it will get a lot higher than this. Yeah, we just wanted to compare apple to apples. So it's the exactly same sample. It's higher. It's not. There are not many more particles. It's just the resolution is better. That's it. So this is not a claim that it adds something to the distribution. It just makes it narrower and more identifiable. That's it.
You take the detector efficiency into consideration when you're trying to reconstruct the tracks.
No, it actually gets rid of the inefficiencies.
So would that be related to the higher statistics that you get? Because you have.
No, it's not. It's so it's more complicated. Answer is if you have inefficiency in one of the chambers, right? The other chamber doesn't have that same inefficiency in the same place. And since we are using all 6 sectors to train it learns to overcome inefficiencies in the part. So if I go into details, it's too long of a discussion, but no, the issue there is that the conventional algorithm has limitations. It's handwritten algorithm, right? It makes mistakes, actually. Not mistakes, but chi-square is not very indicative at that stage to discern between good and bad tracks. So sometimes mistakes happen. This is inefficiencies of the algorithm.
More questions?
Jose.
How many wires in the depth? I know there's 112 by 6.
Yeah.
How many of wires do you need for activation in order for you to consider that super layer to be amazing here?
Yes, 4.
Okay.
4 out of 6 wires have to be activated along the trajectory to consider it as the same. Yeah.
So things like the criteria you use for to quantize how well the machine, the AI do over the conventional way, while the criteria you use is the statistic you get.
No.
Oh, okay, then what is the criteria?
So criteria, that part I didn't explain it well. It's written on the slides, but I didn't explain it. It's a little bit more complicated because what you have there is not really true positives and false positives as in a normal case. Because what you want to have is you want your good one, because you are dealing not with the one event, positive or negative, but in an ensemble of track candidates. You want your track to be identified, good track to be identified, right? And the second, if you have a false positive, you don't want that false positive to be sharing any segment with identified track and have higher probability. And that's what is shown here. So it's the metrics here. I didn't want to get into details because it's a little bit more complicated. It's not as simple as this is false positive or not, because we are allowing to have false positives in a one event sample as long as they don't have higher probability than a real track, and while having higher probability, they don't share any segment, so the good track doesn't get thrown away. And this is actually the metric showing how well we are doing. Like for convolutional neural networks, is 94%, 99.65% of the time, our good track was identified and had the highest probability of all other identified tracks.
Yeah, I mean comparing with the traditional method.
Yes, comparing with tradition. This is sort of comparing with traditional. Yeah, and then so that's just numbers. The physics distribution is visual gratification of the things that. So this is not the metrics how we measure how well. This is just showing you that this works.
So let's go.
Yes.
In the tracking system, we will have like many tracks, right? For example, do you use like a number of tracks as an input parameter, or the machine learning itself can count there are how many?
No. Again, in the next one, in a convolutional, you'll see. But in this case, no, we counted. We enter every single combination that you see connected line is given to neural network, and it says, okay, this one is not good track. And he says, this one is not good track. And then it says, okay, this one is good track. And then we isolate it, and we keep the ones that he considers good track. Yeah. But on the other, for tomorrow's talk, I have something more complicated that actually improves upon this. And it's a convolutional neural network. And that one, actually, we feed one track combination, two track combination, three track combination. And I have images to show you how the neural network descends these things. So it's going to be a lot more interesting tomorrow.
Okay, I have curiosity. Do you think that this, using machine learning to reconstruct track will actually have an impact on the systematical error at the end of what you measure? I mean, if you can reduce the systematical error.
Oh, absolutely, it reduces systematic
Not
error.
only the statistical, that increase clearly the statistical.
Yeah.
Error. But do you think that also, you have probably some systematical error that comes from the fact that you can have some contamination, right?
Yes.
So probably, I was thinking really that you can improve both statistical. That would be really cool.
Yes, so that's the thing. We kind of had some conversations how to estimate the systematic error that calculated based on the efficiency. We don't know how to address it yet, but the fact that you are increasing your efficiency, and some of the things I didn't want to complicate it for people. We have also extracted for this work. If anybody is curious, they can go online and read the article. I'll put links in the talk. we also have the performance curves that as luminosity increases, how the efficiency behaves. And the slope, we improve it by the factor of 2. And on the next one that I have out, convolutional autoencoding improves even further. So I think, yeah, there are some improvements coming from systematic errors due to this, but we yet don't know how to calculate.
Yeah,
We will-
that's okay.
Yeah.
It's just everything over here. Okay. There's another question there.
I have another question.
Yeah.
Have you given any thought to those particles? Because I mean, when we go into the third or fourth layer, that's when we enter the region for the magnetic field. So those particles that might have hit in super layer 1, 2, and 3, and because of the inventing of they will go out of track.
We are thinking about it, yeah. That will be further improvement. So this is right now a huge improvement on top of conventional, and then we can go after the smaller effects and smaller improvements. Yeah, we're thinking, actually, we thought about it.
Okay, other questions? There are two.
You guys can think about some more questions and ask me tomorrow too, if you still have any.
Okay, so thank you again. It was very